We will continue on the topic of particle physics. So next is Amram from Fermilab.
Yeah, so I'm benefiting, but I'm going after Phil. So I'm also a particle physicist, also on CMS, and I'm going to talk pretty much entirely about anomaly detection, and more as like an overview talk to kind of make it broadly interesting to a general audience, because I know most people here are not particle physics people. And this kind of overview talk is inspired by some direct work with Phil and others, but also this review paper I'm writing with Mikkel and our other collaborator, Marco, of like these kind of collection of methods in particle physics, sometimes called model agnostic searches, sometimes called anomaly detection. I'll kind of use those two words interchangeably. In particle physics, we're interested in studying, what are the elementary particles and forces in the universe? And what we know so far is the standard model, this kind of collection of particles and how they interact, written in quantum field theory. The standard model leaves a lot of open questions, like what is the nature of dark matter and dark energy? What's the origin of matter, antimatter, asymmetry in the universe, and many others? And we hope that new fundamental particles would help answer these questions. The way we investigate them is at the LHC. We collide protons together at really high energies and very, very often, 40 million times a second. And then we get these, build these massive detectors to see what comes out, and we get these beautiful collisions. Phil kind of introduced this, and we had Luke's yesterday, so I'm going very quickly. But I guess the point here is that the data is very complex in its native form, and we have a lot of it because you have 40 million of these collisions happening every second. Any discovery you're hoping to make, which would be a new particle, is going to be very, very rare because otherwise we would have seen it before. So the most recent particle that we discovered, the Higgs, happens in about 1 out of a billion collisions. So you have to be able to pick that out of these like massive data sets in these super high dimensional way. So the way we typically would try to claim a discovery of a new particle test in like kind of this statistical formalism with hypothesis testing is we assume the data is a mixture model of your signal, which is the new particle, and the background, which is essentially everything else. So in this case, the standard model. And so you're assuming that the data is this mixture, and what you care about is that, is the mixture fraction of this alpha, which is like, how much of the data is the signal versus the background, is that 0 or not? And that's kind of the question you're trying to answer of whether there's this new additional component in the data, the signal distribution. And this is normally done with a likelihood ratio test statistic where you're kind of comparing against, alpha not 0 versus alpha 0, and you profile for nuisances and stuff like that. And this is kind of a high stakes claim that we would like to make if there is a new fundamental particle. So we require really high statistical evidence to be able to make claims like that. So 5 seconds. So what the challenge in doing this is that these probability distributions are not well known in high dimensions. Sometimes not even well known in low dimensions, but not well known really. So the classic solution is, we have this naturally really high dimensional data. Let's collapse this down to a 1D distribution that we do understand. This is kind of the bump hunt. This is how the Higgs was discovered. It's how many other particles have been discovered. And so what we're saying is, okay, I have this really natively high dimensional thing, and I'm going to pick this one observable where I can kind of understand the distribution, which is the invariant mass of 2 photons in this case. We assume, okay, I'm looking for the Higgs boson that decays into 2 photons. I'm just going to look at that one variable, even though natively the data is like, 1,000 dimensional or whatever. But maybe I'm like, okay, I do still want to use some fact of that high dimensional information. I'll like, you apply some selection criteria and say, okay, I'm only going to look at collisions where I produce 2 photons, and that's going to get rid of a lot of information. Maybe I want to apply some quality selection on those photons or something. So I'm going to apply some selection criteria on the high dimensional thing to try to use some of the information that I know is there. But the final hypothesis test is still going to be in 1 dimension because that's all I can really model the probability distributions in. And then we use kind of these like analytic parametric functional forms to describe that the shape of the signal is like, something close to a Gaussian. And then you have the background you assume is some, smoothly falling distribution that we can like parameterize. So this is like the classic way to do it. Now, commonly, people are using supervised machine learning for this and saying, okay, I don't want to just like kind of waste all that nice high dimensional information. Let me pick this 1-dimensional observable that I'm going to do this kind of final hypothesis test on very, very carefully. And I'll train a machine learning classifier to identify Higgs bosons versus everything else. And the 1D observable that I'll do my final statistical test on is like the distribution of that classification score of that neural network. So that should be, close to optimal if your, hypothesis is nice and simple of like the thing I want to look at. Okay. So, that's just kind of picking some small subset of the high dimensional space and saying, I want to look here for the potential of a signal. Okay, so we've done this a lot of looking for new particles, picking some corner of this high dimensional space and saying, is there a new particle here? Is there not? Is there not? And none so far. And then we get these plots that are, particle physicists recognize as exclusion plots saying like, okay, this type of particle with these properties, like this mass and coupling or something, cannot exist. Otherwise, we would have observed it, which is, great and useful scientific information, ruling out the existence of things, but we want to make discoveries. So we've probably done, order thousands of these, and before, we haven't been in this LM automated world. So each of these has taken around 3 person years to kind of look for this type of new particle or this type of new particle or whatever. So there's a huge amount of work that's gone into doing this. But we know the space of possibilities of new particles that could be living in the data is much, much bigger than this, and much bigger than we could ever, fully encapsulate with, human things. And even in like the, LLM automated future, we still have to tell the LLM like the theory of physics to go look for, right? Like we have to give it the hypothesis to test, even if it was a perfect, like automated discovery pipeline. And what if we just haven't thought of the right thing? Nature has surprised us many, many times before, so we have to be open to the possibility of surprise. So what if we're not looking in the right places and therefore missing these discoveries that could be in the data because it's, so high dimensional and so vast, and we've been looking at these narrow slices. So this can, very easily happen, is that you're training your classifier to look in one region and there's some signal in some other region that you didn't think to go look for, and you just like entirely miss it. And this is not kind of a purely academic thought. In fundamental physics, we've been greatly surprised before. So in the start of like kind of particle physics going all the way back to radioactivity, discovery of the muon, discovery of the CMB were all very, very surprising at the time. And were kind of only possible because they were in these like, low data kind of simple data environment where they're like hand looking at images of cosmic rays is how they discover the muon. They're like, whoa, that's weird. And when you only have 10 images, you can like stare at them and see that the weird thing pops out. When you have billions and billions of collisions, how are you going to notice the weird thing if you don't know exactly what you're looking for? Okay, so the hope here is that these new machine learning methods can reignite the possibility of like genuine surprise discoveries in these modern complex high dimensional high data experiments. So this kind of landscape of anomaly detection, going back to this mixture model, we have the background and we have the signal. And so the landscape is here. Okay, what assumptions am I going to make about the signal, and what assumptions am I going to make about the background? How strongly I'm going to assume. And so I'm going to kind of be in the regime where we want to assume as little as possible about the signal. And then the way we're going to categorize it, just methods, is like, how well do I know the background? How well do I understand the background probability distribution? So before that, we talk about types of anomalies. So something that's, I think, qualitatively a little bit different in high energy physics as opposed to other anomaly detection applications sometimes is that in high energy physics, we're often very interested in this idea of collective anomaly detection. So is there like a collection of data points? If there's some new particle, it probably wouldn't be just produced in one singular collision. It'd be produced multiple times because we're kind of running the same experiment many, many times. So you would have a collection of events that kind of deviate together from the reference distribution, the background. And that's different than like a single outlying point that's just kind of out of distribution, which is sometimes what people consider anomaly detection in other subfields. And so you can have, in some rare cases, you can have that, but normally, because quantum mechanics is random, like the standard model kind of covers almost everywhere, at least to some extent. It just becomes increasingly rare. So what you need really to claim a discovery is some collection of events, not just like one singular event where you could claim a discovery. Okay, so we kind of put together this flow chart for this review of like when you should use these different anomaly detection methods, and really comes down to like what assumptions are you able to make about the background. So if you had if you're in a regime where you actually really understand the background probability distribution, and you have some, either that's known analytically or more commonly in high energy physics, you have some really good reference model, like you really trust your simulator or something like that. What should you do? So in this case, we're kind of recommending this like class of 2 sample tests. So 2 sample tests is like you have 2 different data distributions, and you're trying to test, are these coming from the same underlying probability distribution or not? Like I have 2 kind of data sets. And so in the classical case, there's like lots of things that are well studied, and when you just have like one variable, but we want to do this in high dimensions. So recently, there's like been several works using the idea of, okay, we can use these machine learning based classifiers to test whether these two kind of distributions are the same or not. So the basic idea is you just train a classifier to distinguish between those two distributions. If the classifier is able to do that, then there's probably something different, and you have to be a little bit formal about it. But that's a basic idea. How we would apply this to these model agnostic searches or anomaly detections, you say, okay, one of these distributions is my reference, my background, which I'm assuming I understand pretty well in this regime. And the other distribution is the data. So if I train a classifier to distinguish between the actual data and my model of everything that should be in the data, and if it can find some difference, that's evidence that there's something in the data that I don't understand, right? And of course, this really is going to rely on the fact that I have a good reference model in that case. So the method in which kind of first formalized this hypothesis two-sample test in particle physics is called this new physics learning machine that Phil talked about. And so you're training this classifier between the reference sample and the data, and that's learning something like the likelihood ratio. And then you formulate this test statistic, which isn't just exactly the likelihood ratio, but with some exponentials and stuff. But I don't think the details are super important. But this is kind of how you take this classifier. You don't just look at the classification accuracy. You actually build a formal statistical observable to do your metric. One thing that I think is important to note of why is this might be a good thing to do at all is, okay, when you train the classifier between the data mixture and the reference, what it's learning is some monotonic rescaling of the likelihood ratio of that, right? And the likelihood ratio between that mixture model and the reference is just monotonically related to the likelihood ratio between the signal component and the reference, which is, kind of the optimal, from the name Pearson lemma, is like the optimal thing to distinguish between the signal hypothesis and the background hypothesis in the simple case. So that's why learning in this way is probably a reasonable thing to do. Okay, so this is kind of formalized in this MPLM framework. So you have your reference sample in high energy physics. It's probably from a simulator. You have your observed data sample. You train a classifier to distinguish them, and it's going to learn this density ratio between those, and you use that to compute the test statistic. But of course, what do I do with that test statistic? In order to get a p-value, you have to understand the null distribution, right? And that in the MPLM world, you just bootstrap your reference model many, many times and say, okay, I'm going to assume this, was my data set if I just bootstrap from the reference model. So under the null hypothesis that the data is just coming from the reference model, you can generate many bootstraps and kind of empirically, build this distribution of test statistics you would expect to see. Another way to do it would be to randomly permute the background probability and the reference and the data, because under the hypothesis they're the same. That also is a way to generate the null. Okay. So that was kind of the first class of methods. The other class of methods is, okay, what do I do if I don't have this highly accurate reference distribution? And there's kind of two methods I'll talk about there. But then if I do, a big qualitative difference is if I don't have this highly accurate reference distribution, the final statistical test I do has to be, we don't have a general method of how you do this, right? You have to make some sort of assumption. And so we're saying it's application specific. And I'll talk about, some applications we've done in high energy physics of how you do this, but we don't have a general formulation. But you do something to kind of down select the data to be in some kind of subspace of the data where you think you might be more sensitive to the signal. And then you apply kind of statistical tests that we understand well in high energy physics. Okay. So the two kind of main classes of how we're doing this are outlier detection and weak supervision. And at the end, yeah, as I said before, you either have to do some domain-specific statistical tests that you still understand how to do, or you could just flag these events for humans to look at later or something like that. Okay, so the weak supervision thing is essentially the same as what MPLM is doing, except now I'm not assuming I have a perfect reference. I'm just assuming, okay, I have two mixtures, and one of these mixtures could be my data, and the other mixture could be my kind of imperfect reference. And that imperfect reference, I could have bootstrapped from the data using some various techniques of generative models and something like that. If I didn't have a good simulator or something like that. But the point here is that I have some imperfect reference and then some portion of the data I think might have a signal in it. I train a classifier, distinguish between the two. It learns the likelihood ratio. And I don't use that to do a statistical test, but I use that to kind of down select the data and say, okay, this classifier now can identify the signal that's different between it and it's like in my kind of maybe crappy reference. And then I just cut away all the events that have a really low classifier score that look like they're just from the reference. Now I'm in some subspace where, I think there might be more signal and I can do my statistical test there. The other method, which I kind of consider the method of last resort, is outlier detection. So in here, you're not attempting to learn the likelihood ratio. You're learning something that is like kind of essentially just the background probability density. And you can either learn that explicitly with something like a normalizing flow or anything like that. Or, if you just train an autoencoder or a VAE, which people use often, I would say that's like, and then use the reconstruction loss as kind of an outlier detection method. I would say that's kind of like implicitly learning the background probability distribution or something related to it because it's only learning of the background. The real challenge here and why I consider it a method of last resort is the coordinate invariance problem. So, probability distributions, probability densities are not invariant under any coordinate transformation that has a Jacobian. So anything that's nonlinear. Now, likelihood ratios of densities are because the Jacobian cancels in the numerator and the denominator. So that means that if you say that something is low density, that's low density under some coordinate system, right? And so which means that, whatever data representation you're using to learn the density and then saying that that's like a low density, therefore anomalous, is like a really large inductive bias you're applying for where anomalies are going to show up. You're saying in this data representation, anomalies are in the tails of this distribution, which maybe is a reasonable assumption, but it depends on what variables you picked and how you choose to represent the data. Okay, so the case study of where you would apply this kind of second formalism of like, okay, I'm going to down select my data and then do a kind of normal hypothesis test are these resonance searches. So we're going back to this bump hunt thing, but we're assuming we're in some regime where I have like too much background. The background probability distribution, my data set is overwhelmed by the background probability distribution so that I can't see the signal bump. And you might miss a discovery like that. There's some small component of the signal living in the data, but it's like orders of magnitude below the background, so you might miss it. So then the idea of these like down selection methods is like only going to select, in this case, jets that look anomalous, which is one type of thing that we look at the LHC, but just like I'm going to down select my data somehow in this model agnostic way, and then do the same bump hunt hypothesis test I already know how to do, but now I'm doing it on a sub portion of the data where I have a greater signal fraction, like alpha is larger, so that I have greater power to detect it. So that's kind of the idea behind these anomaly detection methods. The real pitfall here is whatever down selection you do of the data can't mess up the statistical test you want to do in the end, right? So if we're doing this bump hunt statistical test, we're requiring like the shape difference between we're requiring that I understand the shape of the background and the signal. The key thing here is if my down selection somehow changes the shape of the background such that it no longer has this like smoothly falling shape that I assumed, that's going to completely mess up the statistical test I'll do at the end, right? Because now I don't claim to understand the background distribution. And the worst case is if I somehow preferentially select background events that are like in the region of the signal. So my background used to be smoothly falling. Now it has a peak that kind of looks like the signal. So I could, if I had just assumed that I still was like the background distribution is still like this and I try to fit this data, then I would fit some large signal component like that. So this is called like mass sculpting in the higher G physics lingo. And this is like the really thing you have to avoid because otherwise you'll just completely bias yourself when claim false discoveries. Okay, so how are you going to validate that you aren't doing this? You're not messing up the statistical test you want to do later. So you can do methods in Monte Carlo, even when it's like imperfect, you can, deploy your methods there and convince yourself you kind of understand its biases and these sort of things. So that's nice. You understand everything, but you're limited by, we know our Monte Carlo is imperfect. So if there was some mode of the data that wasn't captured in the Monte Carlo that maybe was causing a bias, you wouldn't notice it. And also, actually, we also often have much more data than we actually have simulations because there's billions and billions and billions of data events, and we have some limited CPU budget to generate our simulations. So you kind of are sometimes limited by the size of your simulator, even though you think it might be infinite in theory. You could go to some portion of the data where you don't expect to see any anomaly based on prior studies or based on some physical principles and kind of run your algorithms there and convince yourself you kind of understand the null distribution. So that has some pros, but then you really often have to make some sort of assumption to say that this region of the data doesn't have any anomalies in it, and it's often difficult to find a region of the data where that looks similar to where you think the anomalies are. So there's be some distribution shift when you in the other region, and so it's not an apples to apples comparison. You can also run on synthetic data sets, which are like cheap to sample from, and so you can like get infinite statistics. But of course, then you're worried about if from some generative model or something like that. And if you train that generative model in the right way, in theory, there could be very small domain shift. But you always worry about just potential artifacts in the generative model that you would bias things or make you have poor conclusions. Okay, and then you want to validate this on true positives. So can we actually find signals in the data? So you can test this in simulation by injecting like benchmark signals into some either into simulated data or into the control region, kind of running the process there. And that's great to do. But people in high energy physics are especially convinced by doing things just in the data, so that you can't claim to have kind of used your bias that what the signal was, or kind of doctor things in simulation. So sometimes you can use kind of known rare processes in the data and kind of deploy your algorithm there and say and try and find those anomalies again and show. So Phil was showing this like rediscovery of the top quark, and here's kind of a prettier plot version of that. So you start with this distribution and the anomaly. It's not really an anomaly. We know that there are top quarks in the standard model, but in this region of the data, it's like a very, very small contribution that you can't really easily see. It's like less than 1%. And then you apply your anomaly detection to select, things that look different than the normal background in blue here. And now you greatly enhance the contribution of this other of top quarks. And so you can very clearly, see some mode of the data that you were totally missing before. Okay, so then, but whenever you evaluate the performance of these anomaly detection methods, I think you need to keep in mind the context of them. So I think they're never going to be optimal, right? So if you know exactly what you're looking for, right, you should just train the supervised classifier to look for that. That's going to be better than these like kind of more general purpose methods for sure. So that's a useful baseline to keep in mind. So that was in this plot is this plot is you're plotting kind of the p-value you get from the statistical test of the anomaly detection method as a function of the size of the signals, like the size of alpha in the particle physics units of cross section. And what you're hoping is you get a high p-value at a low alpha. And we're comparing various different anomaly detection methods that we employed in CMS here against each other and also against the supervised baseline. But then the other baseline we compare to is just the regular bump hunt if you didn't use any anomaly detection. And that's the black line here. So the claim I want to make is that in order for the anomaly detection to be useful, you just have to do better than the black line. You have to be able to do better than making no kind of use of these fancy machine learning things, and you have to kind of set expectations that you're never going to reach the gray line. You're never going to be as good as if you know exactly what you're looking for. But if you're doing better than the black line, then you're doing something useful, and you're doing this not just on one signal, but many signals. Okay, so I think what's exciting in the last few years, we've kind of gone from these methods kind of being just proof of concept or explored in simulation to actually results on data that are put out by these large experimental collaborations, which, as Phil was telling us, have really lengthy review processes. So they've been like very thoroughly vetted. And so it's kind of, this is a growing interest in the larger high energy physics community of deploying these methods, because people are seeing the power of this approach, that they are actually sensitive to many signals at once. And it's kind of a new way to look at our data to try to make discoveries. And because Lucas is gone, then I can include more CMS results and Atlas results. They have other ones. Okay, there's pretty pictures you can make of what what these anomalies actually look like, but none of them are statistically significant, so maybe it's not worth spending too much time on. But they're pretty to look at, and you can high energy physicists can look at this and try to understand what was anomalous about this. What did this machine learning algorithm do? And that if you actually saw some excess, so you saw some anomaly at 5 sigma, this would be a really crucial step of the kind of full chain here is like, okay, what you're saying, this is something that's not in the standard model. What is it? Is this just some glitch with our detector? Is this just, some weird experimental effect that we didn't know about or already knew about or whatever? So being able to interpret what is this anomaly is really important. And I think, we did some studies of that in CMS showing that we can kind of do this, but I think more work is probably needed in this direction because it's not always super easy in high dimensional spaces to interpret like what is happening. And then if you don't see anything, particle physicists really like putting out these exclusion limits, saying, okay, I analyzed the data and I didn't discover any new particles, but I can say that this new particle cannot exist with this coupling because otherwise we would have seen it in this experiment. And that's really useful feedback to the broader community of like, oh, the supersymmetric top quark has to be at least this heavy or whatever, because that kind of informs our global picture of what fundamental particles exist or don't exist and can help guide what experiments or analyses we do in the future. And doing this in the anomaly detection case is very difficult. We have some methods, but they're really computationally costly. And right now you can only do it like internally within the collaboration. We can't yet like release something. And so maybe 5 years from now, someone else comes up with some crazy model of a new particle and they want to test, is this already ruled out by that anomaly detection search? Right now, they can't do that. So having methods that make it like easy to assess post hoc, like whether this search would have found that anomaly or not, I think is really open challenge for the field. So that was the conclusion. I just wanted to give an overview of this kind of area of work of model agnostic methods. So the methods kind of differ in their flavor in terms of what assumptions they make about the signal versus the background. And I think there's different methods you should employ based on what assumptions you're able to make. The challenges of validation under the null of like, can you really trust the p-values that you're getting? And then also assessing the sensitivity to different signals and like understanding how the choices you're making in terms of like how you parameterize your neural network or how you pre-train it or whatever, how that ultimately impacts like what sensitivity or power you have to which signals. I think that connection is a little bit unclear right now. We make some reasonable choices, and then we evaluate our sensitivity. Understanding the trade-offs better, I think, would be good. And then interpreting, if you had some interpreting both in the case of a positive discovery or in the case of no positive discovery, I think are also future work directions. Thank you.